Okay guys, good morning. We need to make some good progress today. I mentioned earlier by email we would do some looking at the Diels-Alder. We're a little bit behind. I don't want to do that quite yet. We may try to do that in lab or whatnot. We need to push ahead here. And then in another page or two there'll be some review. You need to start working on, if you haven't already, questions. Questions on the second page of the handout. There's questions on the next couple of pages of the handout. And then we'll be moving on to the elimination. You need to be working problems, asking questions. Okay, we're looking at nitrogen as a nucleophile. We did direct alkylation. We looked at some problems with that. We did an indirect using azide. And then the azide, the N3, can be basically reduced down to the NH2. This brings us to the idea of quaternary ammonium. Good morning, guys. Thanks for joining us. This is a tertiary amine. It's sterically hindered. It can still do SN2 though, with heat. Okay? It's not easy, but it can be done. These electrons come in here and do an SN2, kick that off. Nitrogen now bonded to that carbon. We made that bond right there. The nitrogen is now positive. We kick off the Br minus, right? These arrows should mean something, and we generate Br minus. This is it. There's no H here to lose to go neutral. The nitrogen is now bonded to 4 carbons. It's a quaternary nitrogen, quaternary ammonium, since it's a positive charge. If you include a base, there's no H to remove. This can be an end product called a quat, an abbreviated name. Nitrogen's positive. It's got to have a minus sitting with it. Okay, and the minus would just be the leaving group. So it's an ionic product. A good old SN2 reaction, right? Quats are seen in a lot of places. For example, in biochem, you see this quat here. Now there's no anion shown with it. There's got to be one, okay? Especially if you get it in pure form. Choline, okay? It's very important in biochemistry. Precursor to acetylcholine, or some people say acetylcholine. Okay, quaternary ammonium. This guy, nitrogen with 2 methyls and 2, if you count that up, that's 2 decyl groups, 10 carbons each. Didecyl, dimethyl ammonium chloride. It's a quaternary ammonium salt. This is used as an antibacterial. You know, these hand gels, a lot of them just contain ethanol. Some of them, though, will contain some other microbials. A lot of microbials are like quats. Actually, this one right here, if you go over to the YMCA and you're working out over there, they have these little things on the walls for cleaning your hands. If you look on the label, it'll say didecyl dimethyl ammonium chloride. Okay? These things have antimicrobial activity. They probably disrupt the organisms. Okay. What are some other examples of quats? So, how do you make a quat? We just showed you. Of course, this can be made a different way. You could start with maybe these 3 groups on there, and then make that bond, where that carbon has a leaving group and the nitrogen bonds to that carbon. So there could be different ways to make quats. Other examples of quats. The world's most bitter compound is a quaternary ammonium salt. This quaternary nitrogen, positive charge. The anion is not a simple halide, but it's actually a benzoate. So plus and minus. It's called denatonium benzoate. What's it used for? I mentioned they're starting to put it in antifreeze because like pets, cats will drink antifreeze if it's left laying around and then they'll be dead. Even children have drank antifreeze before, and there was a mother who had a child that died, and she really pushed for this being put in antifreeze. And I think the companies have agreed. This way, when someone tries to drink the antifreeze, ooh, they don't just sit there and drink it because it's just bitter. Otherwise, the antifreeze has kind of a pleasant taste, but a very detrimental outcome. Okay, so those are some examples of quats. How do you make them? Okay, so we looked at oxygen nucleophile, sulfur nucleophile, nitrogen nucleophile. What about carbon? Can carbon be a nucleophile? Well, not a standard carbon, because a standard carbon doesn't have a lone pair. You need a lone pair to be a nucleophile in an SN2 or SN1 reaction. Can we get carbon to have a lone pair? Yeah, and we've done this before. What about this alkyne? What if we treat this alkyne with some type of strong base? This H is somewhat acidic. This is where we ended for test 2. You treat this with maybe NaNH2. That's plus and minus, right? These electrons take the H, these stay behind. What do you get? Anion plus ammonia. This is just our acid-base reaction. You remember that terminal alkynes have some acidity. We can deprotonate them. And when you do this, what do you now have? You have a carbon with a lone pair. This can be a nucleophile. Now you throw in some type of substrate with a leaving group, maybe just ethyl iodide, and these electrons will then come in here and kick this off. Good old SN2, and you get that bond formed. So you made a carbon-carbon bond. We call these guys, if you remember, acetylide anions. They can be generated. So the first thing is you have to generate a nucleophile from a terminal alkyne. And now our product, still an alkyne, but now it's an internal alkyne. So that's a common reaction that you see with alkynes. Actually, as you look back at the alkyne handout at the very bottom, it alluded to that we would see this later. Cyanide anions. For example, you take this here, react it with KCN and DMSO. DMSO is just a common solvent. By definition, it's sort of inert. It's a polar solvent. If you look back at the solvent list I gave you during week 1, I think it's on that solvent list. Okay. What do we have here? KCN, that's plus and minus. Cyanide. The structure of cyanide is that. And it contains the carbanion. Okay? Alkylation of carbanions. Cyanide's a good nucleophile as an anion. These electrons come in here and kick off the leaving group. Good old SN2. Now we're going to have a cyanide attached to this carbon, but I'm showing stereochemistry. What do we expect in terms of stereochemistry? Backside attack, right? What do you expect in terms of stereochemistry here? SN2 gives? Starts with an N. Somebody?
Inversion.
Inversion, yes. That's the terminology. You need to know the terminology. SN2 gives inversion. And so the product here is going to be going to be that. Will inform this.
SN1.
What do you say? It's the same thing. It's the same thing. Yeah, those are the same thing. Okay? A lot of times I'll draw the product like this and someone will say, well, I thought you got inversion. I'm like, it did invert. It's the same thing. We can do RS. What is this? Bromine, carbon here, methyl. This is R. Carbon with nitrogen is going to be carbon with other things. It's 1, 2, 3. It's to the right, but the H is forward. So what is this? That's S. Well, that's also it's the same thing. Okay. Now, I could have just drawn it like this and left it at that, but what I want to get at is please don't fall into the trap that just because you see a bold that it's got to be dashed. You can draw this compound bolded, just like I can draw my hand with the thumb back or forward. Either way, it's still the right hand. Okay? So that's an example of a carbanion doing a substitution. Now what's on the carbon? An alkyl group. Now of course this is triple bond N, okay, with a lone pair. A lot of times this is shown as CN, abbreviated or condensed, right? But we know that's triple bond to N, nitrogen has a lone pair. So that's actually an example of carbanion. Now, cyanide, typically you just buy. You don't have to make the anion. You know, buy it. Okay, so those are a couple of examples of carbanions acting as nucleophiles. There's 1,000,001 other examples, but we covered some basic standard atoms. Let's look at this reaction. You take this compound and heat it in ethanol, you get these two products plus HBr. Is this a substitution reaction? Well, if you just focus on this product, this is this, bromine attached here, but now instead of bromine, it's the O-ethyl attached there. So we replaced the bromine. We substituted it with something else. Yeah, it's a substitution reaction. Now, when your nucleophile is neutral, you're going to have to lose an H for this to be neutral. So that's just lost an H. So this is a substitution. Is this an SN1 or SN2 though? Flat white SN1.
Because it's a weak
Yes?
Name is escaping, but it's.
Nucleophile.
Yeah, nucleophile.
Weak nucleophile. This is the carbon with the leaving group. This apparently reacted. It's the nucleophile. Strong or weak? Weak. We discussed that last time, right? Okay. So is it SN2? Can you do SN2 with a weak nucleophile? No. Looks like it's SN1. Now we're also looking at regiochemistry because we're also, somehow the nucleophile is bonding over here. How in the world would that happen? Whenever you do an SN2, the nucleophile bonds where the leaving group is. If we're doing SN2, the nucleophile should be here because it comes in here and kicks it off. It ain't going to come in here and kick that off. How can we get the nucleophile attached to the other carbon?
Alkyl shift.
We've already said the mechanism is SN1. What's the key intermediate in an SN1?
Carbocation.
Carbocation. What are they prone to doing?
Alkyl shift.
Rearranging. Yeah, there's a rearrangement in here, which suggests it must be a carbocation. And since it's carbocation, SN1. So that's another reason that this looks like an SN1. You don't get rearrangements with SN2. SN2 is nucleophile bonds to the carbon with the leaving group. That's it. Okay. So let's do mechanism here. What's the first step? We just put this in ethanol and heat it. What's the first step?
Ionize the bromine.
Ionizing? Yes. Bromine just leaving. And if it just leaves, we get this cation plus Br minus. As we mentioned earlier, leaving groups can just ionize off. You put HBr in water, what does the bromine do? It ionizes away from the H. Creates H plus and Br minus. Polar solvents facilitate this. Well, that's a polar solvent. Okay? How can we get the first product?
Just attach the
Ethanol, which is a weak nucleophile, but it's still going to be a nucleophile. And adds here. What does that give? Oxygen is now bonded here. There's one lone pair left. There's an H there, and there's an ethyl there. So the lone pair may bond to carbon. And this is a positive charge now. And how do we get home? Somebody's got to take the H. What takes the H?
Br minus.
This takes the H, leaves the lone pair behind. We get that plus HBr. Now for that reaction to give that product, we had two intermediates. Okay, we had 3 steps. Which is the rate determining step?
First.
Formation of carbocation is typically the rate determining step. And what general mechanism did we just do here? It's a substitution. Is that an SN1 or SN2?
SN.
It's an SN1. Just like we showed a couple of days ago. Because here's the rate determining step. Of the 2 reactants, which one is involved in this step? Only that one. The nucleophile is not involved in this rate determining step. Only one substrate. That's why it's called SN1. Slow. The nucleophile adding is actually fast, easy compared. Because this is fast and easy, you don't have to have a strong nucleophile. A weak nucleophile can do this. this guy's lazy. It's not going to do an SN2. Because getting this to come in here and attack here, there's only a partial positive there. This guy doesn't have enough electron density to be attracted there, apparently. Now, if it was a minus, it would be attracted there and you'd be doing SN2. But it's not. But once you make the cation, now that guy gets excited and gets off the sofa and does something. Well, how do we get the other product? What are carbocations prone to do? There's an H there. You can do a hydride shift. If you do a hydride shift, you get this cation. We went from secondary to tertiary. Yeah? And then you can get home from there, because to get the middle structure, ethanol adds here, then you lose the H, and you make this plus HCl. Right? Now this reaction could give mixtures. It all depends on how fast it rearranges. For us, like I think we said earlier with alkene reactions, if this was a purely predicted product, I would want you to say this is major, the major product. Because if you can rearrange, always rearrange, and call that the major product. If it's going to rearrange, then do that. You only get rearrangements from SN1 because only SN1 involves cations. SN2 does not involve a carbocation. SN2 does not give rearrangements. Now, this reaction up here is called a solvolysis reaction because it looks like it's just reacting with a solvent. Ethanol is kind of just a solvent. It's reacting with the solvent. So here it's not strictly a solvent, it's actually a reactant, but it's where solvent is a reactant. And when the solvent actually reacts, it's called a solvolysis reaction. First person who ever did this was like, it's like my solvent reacted. Well, it did. So that's the terminology there, a solvolysis reaction. And solvents are neutral molecules, so it's typically an SN1 reaction. Now what if you did this solvolysis reaction down here and you had stereochemistry involved? What would the products look like?
The stereochemistry would change.
What do you mean the stereochemistry would not change?
If it's an SN1 reaction, SN2 reaction change stereochemistry.
SN1 doesn't change stereochemistry? Racemic. How do you attack a cation? From front, back? Both sides. You would get both. So if we drew this, we're going to redraw the products, but with stereochemistry, same products. We're going to keep the stereochemistry. That would be bolded. But this would be racemic. Which means I got two structures. I got one where this is bold and that's bold. And I got one where this is bold and that's dashed. Because when this came in, it attacked from the front and the back, or the back. Now what would the other product be? That'd be the same thing. Why? Because that product's not chiral. Doesn't matter how you draw that one. Not chiral. I mean, yes, when this gets attacked, it gets attacked from both sides, but regardless of which side it gets attacked, it's the same product. Right? I could draw this one dash to one bold, but it's the same exact product. So I'm not even going to show anything, right? What is the rate equation for the above solvolysis reaction? Rate equals what?
K times
Some type of constant, then what?
concentration product.
I'm going to call it alkyl bromide. Anything else? That's it. It's SN1. What type of nucleophiles react strictly by SN1 mechanism? Weak. What if your nucleophile was strong? Would you be doing SN1? Why not? Can a strong not do an SN1? Theoretically, it can. I mean, why wouldn't a strong attack the carbocation? Why, when your nucleophile is strong, is it not SN1 usually? If this was strong, what would have happened first? Backside attack. Why?
It's fast.
Strong nucleophiles are bullies. They have to stick their nose in backside. Okay? If this was strong, it's like, here I come. The strong nucleophile won't wait for the bromine to leave and ionize. It won't wait. It pushes the reaction bimolecular. Here I come, backside. You don't have time to ionize. On the other hand, the weak nucleophile, it ain't going to do anything. So only thing the reaction can do is just ionize. Because if that doesn't happen, that lazy nucleophile certainly ain't going to get off the sofa and do anything. Okay. Summing it up. Substrates relieving group on primary carbon, only SN2, right? You never make a primary carbocation, so you never do SN1. Substrates relieving group on tertiary carbon, only SN1. Because we said you never do SN2 on a tertiary halide or tertiary carbon relieving group, right? So we've said all this. Substrates relieving group on secondary can undergo either. And you may have to use other information to determine. For example, up top, the reaction up top, the leaving group is on a secondary carbon. You could theoretically do either, but how do we know it's SN1?
Nucleophile.
It's a weak nucleophile. And if we see the outcome and we see rearrangement products, we know it's also SN1. Now, if you're not given much information, you'd have to say, well, they could do either. With strong nucleophiles, reaction will always be bimolecular. Either SN2 Or when we get to elimination, E2. Why? Because strong nucleophiles have to be involved. Here I come, I want to be involved. Not only do I want to be, I am. Boom, I'm involved. Backside attack. Okay? Strong nucleophiles, bimolecular. Weak nucleophiles, which are lazy, reaction will be unimolecular. SN1, or when we get to elimination, E1. Those are lazy. They're not strong enough to be in a rate determining step. But as long as the substrate is secondary and tertiary. Because you wouldn't do SN1 on a primary. Or E1. When we get to elimination, it'll be very similar considerations. Now, of course, if the substrate is primary, thus the reaction will have to be bimolecular. But a bimolecular reaction with a weak nucleophile will be quite difficult. And actually, we said it won't happen. But sometimes you can see it happen, but it's like it'll take a very high temperature. It'll be sort of an exception. Okay, so there's your summary. So let's see what we can do here. What type of mechanism we're looking to do here? And let's predict the product.
SN1.
Somebody says SN1. Why SN1?
Weak nucleophile.
Weak nucleophile. Okay, show the product. You have stereochemistry to consider. Also show the balance reaction. That is, what is the other byproduct? Okay, we've identified this as weak. Looks like it's SN1. Can you do SN1 on this leaving group on secondary?
Yes.
Yeah. Mechanistically, you should be able to do this. I'm just going to show product. Ionization, weak nucleophile attacks. Then you're going to have to lose an H to go neutral. Product is going to be this plus what? What's HBr? And what's the stereochemistry here?
Racemic.
Yes, racemic. Because the cation is attacked from either side. What if we do this with KOH?
SN2.
Our nucleophile is an anion, weak or strong? Strong. SN1 or SN2?
2.
SN2. Since it's SN2, what do we do?
Inversion.
Good old SN2, strong. And we're going to have an OH there instead of a bromine. OH instead of a bromine. But what's the stereochemistry going to be here? It starts with an N.
Inversion.
Inversion. Inversion. Backside attack. These two reactions we've discussed in detail earlier. Every detail we discussed before, so I'm not going to rehash it right now. Look back at your notes. One's SN1, one's an SN2. Mechanism, rate determining step, rate equation, stereochemistry, etc. Okay, there's others down here. I'll let you do that when you're on your own. How about over here? What's the mechanism here?
SN2. SN1.
So what's the mechanism over here?
SN1.
SN1? Anybody think it's SN2? Nobody? Why not SN2?
Tertiary halide.
Tertiary halide, good. You don't do SN2 on tertiary halide. That was with exclamation points, so pretty much that should be a pretty firm statement, right? Okay, so what are we doing? So that's it's what? SN1?
1.
SN1? What kind of nucleophile do we have?
Strong.
Strong. Is it going to be SN1 with a strong nucleophile?
No. Yeah.
Well, if you look at this, the summary page, it said if the nucleophile is strong, the reaction is going to be what? What did it say? Bimolecular? Well, SN1 is not bimolecular, that's unimolecular.
Yeah, but then it says quantity under SN1 with a feature carbon.
Basically, this is neither SN1 or SN2. This is a classical strong nucleophile slash base bimolecular. That's a good statement. Bimolecular, you can't do SN2. Our other bimolecular is E2. This is a classical E2 reaction. You're not going to get either SN1 or SN2 here. And this takes us into elimination. Okay? By the way, the one on the left, what does it look like? Substitution-wise. SN1. You can show the product of that on your own. We'll look back. Okay, there's several down below, including reagents. I think all those are reagents. Reagents would give these products out there. Please do those. Synthesis. Okay? Synthesis. How can you make methamphetamine from this guy? I think that guy over there is Sudafed. How do you make methamphetamine from Sudafed? Okay, on the very back is just another please look at this. We'll look at this hopefully maybe next time. This reaction, what's the purpose of the base? I'm saying that it's SN2, but I'm saying most likely. How would you confirm? Why does it matter? These statements we're making are sort of, our hypotheses. Okay? How would you actually confirm these statements? What type of experimental evidence could you get to confirm?
You could check do the polarimetry tube before and after, so if it's inversion, it would change.
Possibly. The problem is there's really no stereochemistry here. This is apparently racemic. So, but you're onto something. If there was stereochemistry, yeah. Think about that. We'll see what you come up with. How would you confirm that that's SN2? let's move to elimination. Okay? If you haven't already, it's time to be doing problems with substitution and writing your questions down. Okay. Analogous with substitution reactions are our elimination reactions. And elimination are not the opposite of substitution. Elimination is actually the opposite of addition. Go
I
ahead.
have one of those package.
Look at this right here. This is another synthesis of Tamiflu. It actually, by the way, starts with a Diels-Alder reaction. And in their reaction, they're making this product chiral. These are not optically active, so how is this optically active? They're including a chiral catalyst. And that is what is imparting the optical activity. They're getting 97% EE, which is, turn that into a ratio. The other 3% is racemic. So 98.5% of that and only 1.5% of the other enantiomer. That's pretty selective. But that is a Diels-Alder reaction, the synthesis of Tamiflu. But look at this reaction here, 63 to 64. It's iodine. What are we doing here? They're making an alkene. They're removing an H and an I. Okay? 2 H's there, only 1 H there now. So they're removing HI. Now that's sort of in parentheses because that's just formally what's happening now. They're eliminating HI. It's an elimination reaction. It's actually the opposite of our alkene reactions because with alkenes, we can add HI or HBr or something, right? That would be addition. Going this way is elimination. And indeed, elimination reactions typically give alkenes. So you can actually just loop around. The alkene, you can add HI and then you can remove HI and you can just go in a circle. So elimination. They're using DBU, which is a base. Okay, we'll mention it later. THF is just a solvent. And this is called an E2 elimination. You can look back at this. Once we go through this. Okay, just like substitution, we're going to show the generic reaction, and then we'll show a specific one. And then we'll do 2 different mechanisms. General reactions. We got a carbon with a leaving group, just like substitution. Tetrahedral carbon with a leaving group. And we know what type of leaving groups are best, right? It's the same thing. Here we're going to have something with a lone pair. But we're not going to call it a nucleophile, we're going to call it a base. Because it actually is going to take an H. And when something takes an H, we call it a base. When it bonds to a carbon, we call it a nucleophile. And they're pretty much almost identical, although sometimes something can be a better base, and of course nucleophile, because sterics is very important when you're reacting as a nucleophile. Okay, but it's got a lone pair. We're going to get the alkene. The leaving group is going to leave. It's going to take on a lone pair. It may be charged or not, but the base is going to take an H. Now we eliminate HX. Okay, we're eliminating the H and the leaving group. That doesn't mean we form HX because the base takes the H And then the leaving group just sort of exists, maybe as an anion. All right, that's overly generic. Let's look at a specific example. We take this carbon with the bromine leaving group, this guy, which could act as a base, and we could get this alkene plus Br minus. The leaving group came off as Br minus, and now the base has the H. And this is now neutral. We're making alkenes. And what have we removed from this here? We've removed HBr. It's now gone. Because if you look at formula, this is lacking HBr compared to the beginning. So we have eliminated. Why is it called beta elimination? This refers to the H that's removed. Because what H is lost here? Actually, that guy right there. That carbon has two H's. But now there's only one on that carbon. So we've lost an H from that carbon. Compared to the leaving group, the first carbon is called alpha. The second carbon is called beta. You're losing an H from the beta carbon. That's why it's called beta elimination. It refers to where the H is or where it was. So when we remove HBr, we're going to put in a pi bond. Okay, so what are possible mechanisms for this? The first one we're going to do, I think here I went ahead and named it. I don't know if I did that when we did substitution. Let's do E1. And E1 goes like this. The first step of an E1 is the same as the first step of an SN1. And what is that?
Ionization.
Ionization. Leaving group just leaves. And that would give that plus Br minus, right? Now we got to generate Br minus, so we've done that. What are you already thinking about this mechanism? Do you like what we've done? Why not?
Because now we have two members.
Primary cation bad. So we already know, hopefully, that this is not the mechanism for this reaction. But I'm still going to show you in E1. Okay, what do we need to do next? Your two H's here. Now, if these electrons come take an H, and these electrons just move in here, fall in as another bond, and make double bond here. You've got to understand this here. Okay, here's a cation. Carbon, carbon. And this carbon has an H. Okay, somebody take my H. Okay, you acted as a base, took the H. But you left the electrons behind. The electrons just fall in and make pi bond. Okay, double bond. Okay, take the H, these electrons fall in. And when this happens, what do we have? Well, pi bond here gives that, and now the base has the H. So we just did a two-step mechanism to propose how we get this. This step is actually sometimes also called the beta elimination, because this is where you actually take the beta hydrogen. So the whole thing is called beta elimination, but also that specific step is sometimes the specific beta elimination. Okay, two steps. Which one do you think is rate determining? Forming a cation. This is actually fast because we're going back to our neutral product, downhill.
losing the electrons and the oxygen to tag the cation directly.
If this added here, what would that give? Just make this bond you're talking about?
Yeah.
Okay. Is this an elimination problem? If you went from here to here, what type of reaction did we do?
Right. You sit aside.
What type of reaction if you go from here to here? What type of reaction? Is that elimination? Be a substitution problem.
No, but I'm just asking, like, what prevents it from...
I get you. What I'm telling you is, at this point that you've asked is, often substitution competes with elimination. We'll have to talk about that. That'd be a substitution product because comparing this to this, what have we done? We've replaced the bromine with that. We substituted. But in going from here to here, we didn't substitute anything. We removed and we eliminated. Yes? We'll have to talk about that as we go through. Okay, we just did an E1. We're about out of time. Let me finish this up. Why is it called E1? Of the two substrates, how many are involved in the rate determining step?
One.
Is this involved in the rate determining step? No. That's why it's called E1. It's very analogous to SN1, except we do elimination. Now let's down here do E2. Please do a mechanism on your own. E2 is they're both going to be involved in the rate determining step. And actually E2, there's only one step. Unless you're doing some type of activation. That reaction is an E2. Because you wouldn't want to make a primary cation.